Picture this. You've got a cloud-connected factory sensor, and it just detected a bearing failure on a massively critical piece of machinery. An alert is instantly generated, right? But here is the catch. That alert has to travel all the way from the factory floor to a remote AWS server, get processed, and then travel all the way back. That round trip takes 340 milliseconds. And the problem with that? Well, the bearing is already seized. The damage is done. Now, I want you to imagine that exact same sensor, but this time it's equipped with an edge AI gateway. The anomaly is detected, the machine is immediately halted, and an alert is sent out, all locally, in just 16 milliseconds. No cloud, no latency, absolutely no failure. So let's dive right into this explainer and discover exactly how you can design intelligent edge gateways that process real-time sensor data and see how this AIoT edge technology is fundamentally rewriting the rules of industrial networks.
That opening scenario really hits the nail on the head, doesn't it? When we're dealing with industrial safety, autonomous systems, or insanely high-speed manufacturing, you simply cannot tolerate the unpredictable round-trip delays of a traditional cloud-centric architecture. 340 milliseconds might sound fast to a human, but for a high-speed rotor, it's an eternity. You need deterministic latency. You need guaranteed ultra-fast response times that only local, on-site edge processing can actually provide. All right, so here is our roadmap for this explainer. First up, we'll unpack the intelligent edge advantage. Second, we're going to look at exactly when and why cloud IoT hits its limits. Third, we'll map out the complete three-layer edge architecture. And finally, we'll pop the hood and go deep inside the gateway pipeline. Okay, let's kick things off with Section 1, the intelligent edge advantage. For the last decade or so, we've basically been connecting absolutely everything to the internet, pouring all this raw data into central cloud servers and just sitting back waiting for the big data magic to happen. But here's the reality check. The physical world operates on strict constraints that a cloud-only model simply cannot navigate. Just to understand the massive scale of the problem we're facing, look at this number. By 2025, the number of industrial IoT devices is projected to surpass 40 billion. 40 billion! If every single one of those endpoints streams continuous, raw telemetry up to a centralized server, we are going to completely exhaust our global bandwidth infrastructure. It is a mathematical inevitability. Let's actually break down these specific bottlenecks, because the numbers are pretty wild. Take connected cars, for instance. They are generating roughly 25 gigabytes of data per hour. Transmitting all that raw data to the cloud is physically and economically impossible at scale. First, you've got the latency issue we mentioned. 50 to 340 milliseconds is an absolute deal breaker for any closed-loop control system or safety-critical application. Second is the sheer brutal cost of cellular data backhaul. Moving to an edge-first design can actually achieve up to an 80% reduction in these backhaul costs simply by filtering the data at the source. Third is privacy. Let's be real, raw audio, high-res video, or sensitive biometrics often shouldn't even legally leave the premises. And finally, resilience. If a single random internet outage brings your multi-million-dollar production line to a grinding halt, you haven't built a smart factory, you've engineered a catastrophic single point of failure. Which brings us right to Section 2, when cloud IoT hits walls. Because of those physical and economic limits, we are forced to migrate high-stakes data processing directly onto the factory floor. Now, to truly visualize this paradigm shift, I love this analogy. Think of the cloud as the central head office. In the old model, you'd ship every single piece of raw, unopened mail there. The edge, on the other hand, is your on-site manager. They intercept the data locally, they filter out the day-to-day noise, they make tactical split-second decisions, and then they only send a high-level intelligence report up to headquarters. An industrial edge gateway acts exactly like this on-site manager. It ensures your operational continuity and maintains autonomous intelligence, even if the connection to the head office is completely severed. So, how do we actually build this? That's Section 3, the three-layer edge architecture. To build a truly robust system, we structure this new ecosystem into three very distinct architectural layers. We start at the bottom with Layer 1, the perception layer. This is your IoT end nodes, your actuators, and your sensors, generating raw, unadulterated time series data. Maybe they're hooked up via 4 to 20 milliamp analog, Modbus RTU, Ethernet, or Profinet, depending on your environment. Then we move up to Layer 2, the edge gateway layer. This is the hero layer. This is where the AIoT magic actually happens. This intelligent hub ingests those raw streams, extracts the features, runs local AI inference, makes instant decisions, and crucially, it buffers the data in solid-state eMMC storage during network outages so you literally never lose a byte. Finally, we have layer 3, the cloud server layer. Notice I didn't say it's completely gone, but now it only receives compressed, high-value intelligence reports for long-term storage, fleet-wide analytics, remote dashboards, and periodic model retraining. Now, you might be wondering, how do these layers actually talk to each other? Well, we typically use a dual connectivity pattern. LoRaWAN handles the dense, low-power sensor networks locally, while LTE or 4G provides the high-speed uplink and fallback to the cloud. LoRaWAN is absolutely fantastic here at the perception layer because it operates in unlicensed ISM bands and can effortlessly handle thousands of sensors spread over a wide physical area. Then your edge gateway sits in the middle, acting as the smart bridge, using LTE or 4G to securely punch those lightweight, actionable intelligence reports up to your cloud dashboards. All right, let's dive into the most technical and honestly the coolest part of this explainer. Section 4, inside the gateway pipeline. Let's look right under the hood to see exactly how a heavy, chaotic stream of raw data transforms into actionable insight. Every single piece of sensor data flows through a critical 4-step pipeline: data ingestion, scrubbing and filtering, feature extraction, and AI model inference. It's this precise sequence, executed flawlessly by the gateway's software architecture, that allows for localized decisions in just a matter of milliseconds. So let's break down each one of these steps. First up, we have ingestion and scrubbing. The gateway has to simultaneously ingest raw streams from multiple different protocols at once. For example, using rugged industrial hardware like the NXP IMX8, which you'd find in units like the Robustal EG5120, or even microcontroller-class chips like the ESP32-S3, the gateway is doing heavy lifting. We might have vibration data screaming in at 1 kHz, alongside temperature readings arriving every 5 seconds, and maybe acoustic data at 44 kHz. The gateway pulls all of this in, fills any missing values, and aggressively applies digital filters like low pass or band pass to remove outliers. Why? Because the old rule of garbage in, garbage out doubly applies at the edge, where compute power is limited. You absolutely must clean that signal before you try to analyze it. Once we have clean data, we hit step 3, feature extraction. This is the absolute key to edge intelligence, and it brilliantly illustrates the massive economic impact of this architecture. By extracting compact features locally instead of sending everything, we achieve an incredible compression ratio of over 99%. Think about that. Instead of paying cellular providers to transmit roughly 3 megabytes of raw, noisy vibration data per hour for every single sensor, the gateway mathematically transforms that heavy 1 kilohertz stream into just 12 crucial, meaningful feature values, updated every second. But how exactly do we pull those 12 magic values out of the noise? Well, we extract the actual intelligence using methods like fast Fourier transforms, or FFTs, to convert time domain signals into the frequency domain. This reveals the specific resonant frequencies that are a dead giveaway for bearing wear. We also use Wavelet transforms, which capture both time and frequency data simultaneously. That's absolutely perfect for spotting non-stationary signals, like the weird transients you get during a machine's startup or shutdown. On top of that, we compute statistical features, things like the mean, standard deviation, RMS, kurtosis, and peak-to-peak variance, and we do it all in mere microseconds. Finally, we reach step 4, AI model inference. We take those highly compressed, mathematically rich features, and we feed them into a lightweight machine learning model running right there on the local gateway. Now, you have choices here. A shallow neural network might give us the highest detection performance, hitting an F1 score of around 0.94. But if we use a quantized TinyML model, where we shrink the precision of the model weights from heavy 32-bit floats down to snappy 8-bit integers, we get a massive 3 times memory reduction and consume 60% less energy. And the crazy part? We barely lose any accuracy. The F1 score only drops to about 0.92. This is exactly how you run advanced, real-time AI on constrained edge devices without completely melting the processor. So, as we wrap up this explainer, I want to leave you with a fundamental architectural question. As you look at your own IoT projects and deployments, ask yourself, are you wasting your budget backhauling raw noise to the cloud? Or are you building an edge-first architecture that guarantees sub-millisecond intelligence and true operational autonomy? By moving the brain out of the distant cloud and right to the edge of your network, you solve the physics of latency, the harsh economics of bandwidth, and the stark realities of network reliability. It's time to empower your network edges to be proactive on-site managers rather than just expensive raw data couriers. Keep building, keep optimizing, and we will see you on the next explainer.